In calculus, there's basically, there's two massive problems in calc, and I'm gonna very broadly talk about them for like 2 seconds. We're kind of skipping the first section because this is what I'm gonna talk about right now. We're not actually gonna do a bunch of homework on the first section. So most of it is second section stuff, just so you know, and that's the ideas of limits. Now there's two big problems. There's two big problems for calculus that we're gonna be looking at in big depth. One of them is the tangent line problem. And your book does kind of a fancy job, that first section that tells you kind of, stuff you use in pre-calc and that stuff you use in calculus. So if you want to do a little compare and contrast, you can. But I'm just going to kind of elaborate just very quickly the two big massive problems that we'll be talking about. The first one is called the tangent line problem. And the idea of that is I've got some graph that's floating around out here. And who knows what the graph looks like? Maybe something like this. And I want to work on the tangent line of this graph. Now that means that you pick any point on this graph. Let's say I'm talking about this point right here. And I want to find the slope of the tangent line at that point. Okay? Which is going to be not too bad in a little bit. But the tangent line, anybody know what a tangent line is? What it means graphically? A tangent is, the graph of a tangent's got those weird little things. But ever hear somebody going off on a tangent? You ever heard that expression before, right? And I'll explain what that is comes in a second. What a tangent line is, it's a line that only touches the graph at one point. Okay, so a tangent line would be this line right here, and it only hits this one point right there. So that's what they call a tangent line. Okay, you've probably seen that before, but basically the first half of calculus is talking about the tangent line problem. Okay, everything we do is going to be wrapped around this tangent line. Okay. And you guys probably heard that expression, right? Going off on a tangent. And what that usually means is a teacher is, I've related to teachers obviously, but a teacher's talking about something and then you tell them something and then they just go like way off, right? Well, usually kind of where that came from is they were on some talking point, right? And then instead of staying on the graph, like staying on whatever their lesson were, they got offline and just further and further away. And then all of a sudden they're not even close to what the heck they were talking about, right? So that's kind of the idea. That's where that came from. This, the idea of going off on a tangent. So, anyways, now what we're going to do is what's called a limiting process. Okay, we're going to try to find the limit of a bunch of different things, which is kind of a new concept for you guys. But at first, finding the slope of this tangent line is a little bit weird. We're going to have to work on that a little bit. To get there, what we actually do is we look at secant lines. Sorry, that was awesome. All right, so we look at secant lines. So let's say I have this exact same graph. Okay, so I've got some graph that looks something like this, and I want to find the tangent to this point right here, the tangent line. Now the tangent line just goes through one point right there. Now a secant line, you guys heard of that before by chance? A secant line? What a secant line is, it's a line that goes through 2 points. Okay, so that means if I have a secant line, my secant line might go through this point and this point, and so I'm going to have this secant line right here. Okay, that's what they call a secant line. Okay, now as far as what we can do, finding a secant line, finding the slope of that is pretty easy, right? Because if I have 2 points, I can just do either rise over run or my slope intercept or whatever the heck I have to do. That's a pretty easy one to find, right? The tangent line, how the heck are you going to find the slope of that line right there? There's only one point. There's no other point to help you figure out how steep it is, right? So that's kind of the issue that we're having. So what we do is we take the secant line that goes through 2 points, and we know how to do that. And what we do is we move this second point closer and closer and closer to this first line. So let's say I move this point a little bit closer, and it goes right there. I can find the slope of this line. That's right there, right? Okay, and I can continually move this point closer and closer and closer. Eventually I'll move it like right there, so it's pretty darn close, so it's like this. Still a secant line going through a bunch of them. And eventually, as I get closer and closer and closer to that one point, I'm going to get right on the slope of that line. Okay. Now I can't actually find the slope of that line because I only have 1 point. So what I have to do is I have to talk about 2 points and get closer and closer and closer to that 1 point. Okay. And that's the first massive problem that we're going to be looking at. We're going to spend a ton of time on that. Like the rest of this year is going to be wrapped around this problem. Okay. Next year, the second big type of, the second big problem that we'll be looking at is the area problem. Okay. And it's in essence area underneath curves. We've found areas of every different shape that's out there, right? But what if I have a graph that looks something like this? Right? And I want to find the area. And I want to find that area right there. Okay, so who knows what that is? I got no formulas to use. All I have is rectangles and triangles and squares. And That's all I really have, right? So to find the area underneath here, what we actually do is we know how to find the area of a rectangle. Okay, so what I do is I take this guy and I build rectangles on the inside of this guy.
So you do kind of square.
Okay, so I'll build a bunch of rectangles that are on the inside there. Okay? And I just find the area of all those rectangles and add them up together. Now, that's not very accurate, right? Right? You guys would agree with me, right? I got all these chunks that are kind of laying over the top or underneath or something like that. So what I have to do is I have to make more rectangles. And as I make more rectangles, it makes these little spaces smaller, right? And as those get smaller, eventually, if I take this right here and I go to a bunch of rectangles, like an infinite number of rectangles, let's say, right? Then I can actually find the exact area of this, okay? So that's the second big problem that we're doing. We probably won't be doing this until next year, okay? Until the fall of next year, because this is pretty big. So, anyways, those are the two big, massive problems that we'll be looking at in calc. That's pretty much the first section, okay? So I don't think we need to do a bunch of problems on theory like that. So, all right, what we do need to do, though, is talk about this whole limit idea. And the limit idea is taking this number and bumping it up, getting it bigger and bigger and bigger, or getting a value closer to some specific number that I actually want to find. So, what we want to do is start by talking about the limit of certain functions. So let's say I have some function. Yes, there's actually math that's going to happen today. X to the third minus 1, and then this is over x minus 1. Okay, now what I want to do is I just want to visualize what this graph is going to look like. That's my goal. How are we going to visualize what the graph looks like? Okay, I'm glad we agree. Okay, good. So now my calculator is still messed up from doing all the polar and whatnot. So you might want to go back to just your standard graph. So you go back to gradient is always a good thing to put it on functions. Basically, the left column is always good to have all the left columns highlighted. Then you're pretty safe on all your stuff. Okay. Go back to your y equals, and let's just type this in. So we're going to go x to the third, and then minus 1. And then we're going to divide that by x minus 1. Make sure you use parentheses. Oh, whoops. If you don't use parentheses, then it'll get you the wrong thing. Looks like a shape that we've done before, probably, right? Yeah. A little bit. Yeah, kind of looks parabolic if you ask me. Now, if you look at this and you're like, oh wait a second, I got this graph and I got this. What about our domain for this particular one? What's kind of our domain restrictions? What could I not plug in for x? 1. All the numbers not equal to 1, right? If I plug in a 1, I get a 0 on the bottom, and I can't have that. Okay? Well, what I'd like to know is what would the value have been at 1 if I didn't get an undefined answer there. Okay? Right now, I would just say undefined. I can't actually plug in a 1. What I want to do is I want to plug in numbers that are really, really, really close to 1 and see what number that would have been if I could actually have plugged that in. Okay? So what I'm going to do is just take a look at this graph. If you have second calculate value, that's the first one, and you can type in whatever x value that you want. Okay? Well, what I want to find is what happens when x goes to 1. What happens when x is 1? Well, let's type it in. 1. It says y is nothing. Error. Right? So you can't always trust your calculator. We have to figure out what the heck is going on. Now, we can plug in any other point that we want on here, but we know right at x equals 1, there's nothing there. And the idea is, in the calculator you can't see it, but at x equals 1 right here, there's actually a hole in the graph right there. Okay? So you can't see it on your calculator because that's the resolution issues. But I do know that my graph right here is this graph. Let me just get it drawn pretty good. Is right here. And then right at x equals 1, I've got this hole right here. Okay, so that's actually what the graph looks like, even though you can't see it on your calculator. Okay, so you can't always trust that, but you know domain concepts and you know how that's going to work. Yeah.
That happened a couple times on if you zoom in more.
Yeah.
And then all of a sudden there's a break.
Exactly. The more you zoom in, then obviously the resolution is going to get bigger and bigger, and you have a shot at actually seeing what the 0 is. And you can do that if you go to trace, and then you go to, let's say you get really close to x equals 1, which is right about there, and you can zoom in on just that point. If you keep zooming in, eventually you'll see the break. Eventually see the hole. But you got to zoom way in to see it. So way in. But anyway, so the concept is I got to try to figure out what that value is right there at 1. That basically that hole. Okay, what's happening right at this point? When x goes to 1, what are we going towards? Okay, so what I'm going to do is I'm going to build some table, and what I want to do is I want to get really, really, really close to 1, but I can't actually plug in 1. Okay, so my table is going to look something like this. I'm going to have my x values and my y values. And then right here in the center, this is the value I want to find. I want to find 1 for x and then something for y. That's what I'm searching for. So what I'm going to do is I'm going to pick values that are on both sides of 1 that are really, really, really close to 1. Okay? So a number that's really, really close to 1 would be like 1.0001. That would be a number that's really close to 1. Or 1.001. Or 1.01. Or 1.1. Okay? Those are all values that progressively get closer to 1 as I get closer. Okay? Now I go on the other side. Just shy of 1 is 0.999, right? So if I go 0.9999, let's say, and then I go 0.99, and then I go 0.9. Okay? So those are all possible values that I can look at. Now the only problem is I can't actually plug in 1. That's the value that's prohibited for me to plug in. It's not my domain, right? All real numbers not equal to 1. Can't plug it in. Okay? So we're going to put a kind of a question mark here for now and hopefully fill that in. So let's fill in the rest of ours. You can do this in a couple ways. One, you can just go second calculate value and type in whatever value you want. Or you can go to a table and mess with your table sets and do all that stuff. So it's kind of up to you which way you want to go. So let's just go ahead and type in some numbers. So I got 0.9. 0.9 is 2.71. So that's a familiar number. 2.71. So like E or something like that. 0.99. 0.9 I'm getting 2.97. So 2.97. Let's go 0.9999, and I'm getting 2.999. 7. Okay, now let's jump on the other side of that. We're going to go 1.0001, and I get 3.003. 1.001, and I get 3.003. 1.01, 3.03, and then 1.1.
So is it safe to say that 1 is a 3?
Yes, it is. It is so safe to say that we're actually going to write that down. We're going to say 3 is the answer. Okay? Now that's odd. That's odd to say, well, we can't actually plug in 1. But what we're saying is, as I get really close to that concept, obviously the answer is going to be 3 here. This number gets closer and closer and closer to 3, as does this one. So if I were to plug in a 1, even though I can't plug it in because it gives me undefined, the value would actually be 3 there. Okay? So that's what they call the limiting process. You're limiting the numbers that you can pick, and you're trying to get really close to those numbers without actually plugging that number in. Okay? Now how to write that? Zoom way in and it looks like that. And you typed in x equals 1, and did you get that value?
No, I just moved it.
Oh, you just, okay, gotcha. Yeah, eventually when you zoom in far enough, the calculator only has so many digits, and then it just decides to run. So, but you can zoom in a lot and get there, and it'll look fine. So, anyways, now the formal way to write this is, they call this the limiting process. So we're going to write what's called the limit, and this is what it looks like. You're going to go the limit, and I do a lot of scribbling. Let me write it out. I will scribble limit because we're going to write a million of them, and I just cursed that together, so I apologize. Okay, we're going to do the limit, and I don't care if you guys scribble there either. We're going to go the limit as, now the value that we were approaching there, the x value was 1. Okay, I don't know if you see that. The x value was 1. That was kind of our no-no value for this. Okay, so we're actually doing the limit as x approaches 1 of whatever our function is. So our f of x goes after this, which is, I'm just going to write f of x, just to cheat a little bit. Okay, so the limit as x goes to 1 of whatever our function was, that equaled 3. Okay, so a lot of your homework tonight is going to be given a function, trying to find the limit as x approaches some value that you can't literally just plug in, and then you're going to try to build some kind of narrowing gap here to figure out where it's actually going to land. Okay, so 3 is the actual value. Now the tough thing to get here, the tough concept to hang on to, is that even though there's not an actual value there, doesn't mean that the limit can't have a value. Okay, so those two, don't try to connect those two too much. Okay, so because there's a hole there, doesn't mean that there's a value, doesn't mean there's not a value. Those don't connect very, very well, unfortunately. Okay, let's do 1 or 2 of those just real quick. I think we're getting the general idea probably, but let me do just 1 or 2 more. Let's do this one. Let's say our g of x is, let's go x over the square root of x plus 1, and then minus 1. Bless you. And there are some limits that fail to exist. We'll talk about that in a second. Go ahead and try to get that on your calculator real quick. ahead of me, but.
Start there.
Okay, so hopefully you got that graph. Alright, so what would be our domain restriction on this? It would be all real numbers not equal to something. There's a certain value I couldn't plug in there because it'd be bad.
0.
0, right? I can't plug in a 0, right? If I plug in a 0 for x, what happens there? If I get a 0 on the bottom, right? Because I get a 0 plus 1 is 1, square root of 1 is 1, minus 1 is 0. So I get a 0 on the bottom if I plug in a 0. Okay, so what I want to know is I want to know what the limit of this guy is as x approaches 0 of whatever my g of x is. That's what I'm searching for. Okay?
What about like -2?
-2 is not in the domain. It's not even on the graph. So that one, we wouldn't do a limit at that. You couldn't approach you can't approach unreal values if you don't have actual values next to it. Okay? That's like saying what's the value right here, right? Well, the graph isn't even over here, so that won't apply for what we're doing. Okay, it's got to be on the graph. But we do have a hole. Our hole right here would be right here, and that would be pretty much impossible to see unless you can take. You can zoom way in, and you can actually take the coordinate off in your little. I think you can do it in mode, right? Where is it? Oh no, you do it in the format. Yeah. You can do it in format. So you can turn your axes off if you really want to, if you're dying to see that hole there, but unnecessary. There is a hole right at 1, though. Okay, so as far as my graph is concerned, it looks something like this, like that, and I actually have a hole right there. But that's my actual graph right there. Okay. Now the general idea here is I can't actually plug in this value because it's an undefined spot there. But I'm basically going to follow the graph along in this direction right here, and I'm going to follow the graph along in this direction. And if those two arrows run into each other, they get the same value as you go at from both directions. Then that's going to be your limit. Okay. So the limit is x goes to 0. Of the g of x is whatever this height is right here. Okay. So that's what we got to try to search for. Okay. So what we do is we plug in values that are right around 0. Okay. So unfortunately, the way to do this right now is an XY chart. Yeah, right now you know the shortcuts are coming, right? The value that's in the center, is your value that you want, right? So the 0 is what we're finding. We're going to put a question mark, and then do we know it's 1? Looks like it's 2. If I were to just go off the graph, looks like it would be 2. But anyways, let's go ahead and check to see what it actually is. Okay, so we plug in values that progressively get closer to 0. Okay, so close to 0 on the positive side would be like 0.0001, and then 0.001, and then 0.01, and then you get the idea. Okay, here on the left side of it is going to actually be negative numbers, so we're going to get a negative 0.0001, negative 0.001, and then negative 0.1, we'll say. And you don't have to match exact values on both sides. That's not that important, but you just want to get progressively closer to 0. Okay? So let's just go to second calculated value. Type in some values real quick. So 0.0001, and I get 2.0005. And then I'm going to do the one on the other side. I'm going to show you a common mistake people make, negative 0.00. And I get 1.99. Okay? Too often people just pick the ones on both sides of them like this. And they get, all right, I get 1.99 and I get 2, so I know the answer is 2. And they don't do the rest of the values right there. That's bad down the road. Okay, so for now, you want to keep doing this. Sometimes these values are misleading. And I'll show you examples of that as we get a little bit further in. Okay, but do more than just those two values. Okay, so do 0.001 and I get 2.0004, 0.01. You guys get the idea. Sorry to bore you. Here we go. And then you get those values over there. And so you get 2. So the limit as x goes to 0, that's how you read this. The limit as x goes to 0 of g of x is going to be, looks like the value of 2. So 2 is our answer for this guy. Okay? Feeling pretty good? Not too bad, I hope. Okay, let's go a little harder. A couple of the exceptions, obviously. This is where this gets kind of fun. Let's say that our h of x this time is going to equal... I think you guys will be bored if I do that one. Let's do this.
Don't worry, we already are.
I know. See, you're already bored, so that means if I do another one like that, you'll be bored even more. So I'm trying to lessen your 4 factor. Try. All right, graph that. See what it looks like.
Look at Justin's.
Okay, domain for this one's auto number is not equal to 0. You guys probably already got that. I can't plug in a 0 there, get a 0 in the denominator. So this is where we're going to approach our limit for this one. So we want to take the limit as x goes towards 0 of our h of x on this guy. And we want to figure out what value that's actually going to go to. Okay, so unfortunately we have to do our little table here and find the values that are close to 0. So I've got this x and y chart here. I'm going to put the 0 in the middle and then hopefully try to attack it from both sides and see what I'm going to get. So I'm going to go point 0, 0, 1, point 0, 1, and then point 1. See what that looks like. And then negative point 0, 0, 1, negative point 0, 1, and then negative point 1. Those would be decent values. And notice I picked values that are getting like progressively closer by tenths. I multiplied it by 1/10 basically. That's a good option to do. Too many people say 0 and then they go up here and they go like a 1 and then a 2 and then a 3. And those numbers are just way too big to get close to that value. Okay, so that you won't see a pattern if you do those numbers that big. Okay, so you got to pick a little bit smaller numbers. All right, so this is the one that we're looking for, is right at 0. So we're just going to plug some of those values in, and hopefully it works. So let's see what we got. So we're going to go second calculate value, 0.001, and I get a lot of numbers. And then how many that is? 3, 4, 5, 6. Yeah, I got it right. Awesome. I'm assuming it's going to be the same on the other side. I'm pretty sure it is. 2, 3, 4, 5, 6. Plug in a 0.01, and I get, looks like 10,000. So 1, 2, 3, 4, and then same thing over here. Looks like that. And then do the 0.1, probably going to get 100. Yep, looks like 100. And 100. Okay, now we have a small problem here. As I look at this pattern right here, what numbers are these progressively getting closer to? Infinite, right? Is infinity a number? No. So we're not approaching one specific number, which means this limit does not exist. Okay, so this one does not exist.
So if it increases...
Okay, if it increases without bound, is what they call it, if it goes forever, then you're not going to have a limit for that. The limit isn't approaching one specific value. Okay, so this limit does not exist. That's I think that's... Does not exist. Yeah, I know you guys have enough acronyms in your life, I know, I'm sorry. You can put a little 0 with a slash through it too, that's also fine. The problem with this one is, just to watch out for, is too often people get lazy and they do this. Like, oh shoot, I plugged in a really, really small number there, and I got the exact same number on both sides, that must be right. And so then they put 100, or they put 1,000,000 for their answer, right? As the limit. It's not correct, okay? So it's always good to do the ones around it to see where it's actually going towards, okay? All right, the craziest one of all, last one, and then we'll be done with the beginnings of the limits. Let's go back to f of x. This is the other big exception for this one.
Like a herpes monster.
Now keep zooming in. See if you can get a specific value. Okay? Keep zooming in. Oh, that one. Or run your table. You can run a table so you can see what it looks like. Eventually, you guys are going to be able to look at graphs and decide just by looking at a graph what the limit is actually going to be. Okay, some of your homework tonight will be graphically approached. They'll give you a graph and say, what's the limit of this guy? So you just kind of attack from both sides to see what it goes to. Okay. Sometimes they want you to do a table. It just depends on what we're doing. Okay. So our graph here, it's going to be sine of 1 divided by x. Looks something like that. And I'll zoom for the first one.
Okay, that looks like a heartbeat.
Okay, and I'm doing it at 0. It's kind of tough to see right now, so we'll just zoom in real quick. Oops, zoom.
Barcode just keeps zooming.
Yeah, it becomes a barcode eventually, doesn't it? Yep. Now, just gut shot reaction, if I were to look at this graph right here and said, what's the value at 0, I would probably say 0, right? It looks like it's going to eventually run through there, but it doesn't, unfortunately. So we can't always just trust what the graph says. I'm going to hit enter again. And if you're in the zoom in button, you can just keep hitting enter, and it'll keep zooming in for you. Okay, now look at this. Now you can see it a little bit better, right? This value actually skips up like this. It actually doesn't go through this origin point right here. It actually jumps way up here and then picks up back over here. They call these oscillating graphs. Let me just zoom in one more time. But basically what's happening here, if you think about what this function is doing, sine of 1 over x, is I plug in values that are really close to 0. The smaller this number gets right here for x, 1 divided by a really small number, what's going to happen to that? It's going to get really big, right? 1 over a really tiny number gets really big. 1 over 0.00001 is a monster number, right? Well, if I take the sine of that, what's the biggest the sine value is going to get? 1, right? So the highest value it's going to get. So every time if I plug a really big number in here, it's going to get close to 1. It's going to cap it. Okay, now if I do a negative number, right, a negative number right there, it's going to cap it on the other side. So this just keeps bouncing back and forth between almost 1 and then almost negative 1. 1, negative 1, 1, negative 1. Never actually reaches 0, but it gets really close. So it doesn't exist as well for this one because of that oscillating factor. It bounces back and forth. So this one also it does not exist. Okay?
I didn't get that. Sine of something.
If you're not following that, feel free to...
Yeah, still